So let's get started by imagining that we are an end user of the compiler, and our job is to analyze and improve the performance of a program. So how do we go about this? Well, first, we're going to profile our program and identify the hotspots. And for each hotspot, then we will try to determine the bottleneck. For example, we can use hardware performance counters for this. And then, based on this, the user may determine that compiler optimization, X and Y, should help to improve our performance. Then we compile our program, and the compiler, based on its rules and heuristics, will apply some optimizations. Now, these can be different from the ones we had in mind. So how do we find out what the compiler picked? We have a few options. We can try to reverse engineer what the compiler did by disassembling the generated code and going backwards. Now, this is obviously pretty labor intensive, but it's probably still what most people would do. As compiler developers have the option of using the debug output of passes. This is pretty verbose and fairly pass specific. The right answer is to use optimization diagnostics. Optimization diagnostics tell you which optimizations happened, which didn't, and why not. So as we can see, optimization diagnostics play a pretty critical role in this loop back from the compiler to the user. So let's review their state in LLVM. Well, they have been supported for some time, but currently only a small number of passes emit them. And the main use case was the loop vectorizer, to be able to tell whether vectorization happened in a piece of code or not. You activate them with the RPass options, and then they appear in the compiler output, and they look like this. They pretty much look like warnings or errors. The problem is that for large programs, the output of RPass is pretty noisy and unstructured. So here's an example for a module that contains a few hundred lines of code. And notice the scroll bar. This is only a part of the output that's generated. The problem is actually even worse because messages don't appear in any particular order. Remarks for hot and cold code are intermixed. And also messages for successful and failed optimizations are all reported together. So how can we make this information accessible and actionable to our users and even to ourselves? So what I wanted instead is have all the information available in one place. So something like an optimizations dashboard. Being able to review the information at a glance. For example, see the high-level interaction between the different optimizations for targeted low-level debugging. And what I wanted is to have the information well filtered. So the noise level should be minimized by focusing on hot code, for example. And then have an integrated view where you display the hot code and then the optimizations performed on them side by side. So I began implementing these ideas in a new tool I call Optimization Viewer, or OpViewer for short. And this is available upstream. So my approach was designing this tool was to build on top of the existing optimization remarks, so the whole RPass infrastructure, but extend it in two ways. One was to add new optimizations to sort of broaden the scope. And then the ability to output the remarks into a separate data file so that we can then visualize the data and provide it in a structured way. And I picked HTML for this. Initially, with this tool, I was targeting basically the community, ourselves. So I'm assuming a certain level of familiarity with LLVM passes and then the overall pass pipeline structure. So let me introduce the basics of the UI and the workflow with a pretty simple example. So here, what I have is two functions. And in the second one, I have a loop, which can be vectorized if we can inline the first function. So quickly going through the workflow, if you take this module, we just compile it as normal, but pass a new option called fsafe optimization record, which will produce all the optimization remarks into an external data file in YAML format. Then we invoke the opviewer with the generated YAML file, and then pass the directory where we want all the HTML to be generated. In this case, we have a single source module, so we go directly to the source view and open it up in the browser. And then this is what we see. We see the source here, and then we see remarks like this one appear in line under the line that they're referencing. For example, this one is coming from the loop vectorizer. It's right under the header of the for loop, the start of the for loop, and it's also, there's a color coding. In this case, green means that it's a successful optimization. So we're able to vectorize this loop. And then on the right-hand side, you see further details about the optimization. So for example, that we use the vector with a 4 with an interleaved count of 2. And we were able to vectorize this loop because inlining was successful. Also notice here that the right-hand side of the message, so the yellow part, appears always aligned to the expression that it's referring to. So in this case, it's the function call itself. Also, to get that structure and cross-referencing I wanted, we create HTML links basically wherever it makes sense to facilitate further analysis. Besides the green remarks, on this one, there's a white remark, and these are analysis remarks. These are used by optimization passes to emit other interesting analysis results that the user may be interested in. So for example, here, this is the result of the cost model that decided to inline this function. Okay, so how does this look for missed optimizations? For this, I'm just removing the body of accumulate, and then this is the output we see then. As you can see, everything that was green turned into red, because red means a failed optimization. So vectorization failed, because we still have a call instruction in the loop. And the reason we have a call instruction, because inlining has failed, because the definition of the function is unavailable. So before moving on and showing some more complex and interesting examples, I want to go through the changes that I had to add in order to make this work in LLVM. And here, everything that pre-existed this work will appear in blue, and the new components will appear in green. So here I have the pass pipeline shown with the two passes that were in play in the previous example, the inliner and the vectorizer. There's a new analysis pass called optimization remark emitter. And as the name suggests, passes can use this analysis pass to emit optimization remarks. And you do this to an API call like this. Let's look a bit closer. So what we do here is that first we create an object that corresponds to the type of remark we want to create. In this case, we are creating the white analysis remark from the previous example that came from the inliner. So once you created the object, you can parameterize the object with just streaming further parameters into the object. So in this case, for example, we insert a string, which will make up the text of the message. And we can also stream in named value pairs like this. And NV stands for named value. So here, for example, we're directly inserting the IR function under the name callee. And then we just pass the parameterized object to the analysis pass. So the new API provides the old RPass interface. So that's completely unchanged, except what's under the hood has changed. But in addition, it now, with fsave optimization record, produces the YAML output. And for all of this, just like RPass, we enable source line debug info so that we can connect up the remarks with the corresponding source line. So, and with all of this, now we can have records like this in the YAML output, which one-to-one corresponds to the to invocations of the analysis pass. For example, here we create an analysis object, so there's going to be a record of analysis type. It's coming from the inliner. It has a unique identifier. We'll have the debug location of the call. And then here we see the name value pair that we were looking at earlier. This is how we stream that out. So as you can see, the name appears as the name of the field. And currently for IR function, we stream out the name of the function and its location. And this helps us to create the HTML link I was showing earlier. And then we take the YAML file and then pass it through the optimization viewer, which creates the source views and an index page that links them up. So I haven't shown the index page yet. Initially, it looked something like this. And here what you see is effectively a table of contents of all the remarks with the source location, the function that they're coming from, and then the pass that reported it with the usual color coding. The problem is that just like RPass, this is still pretty noisy for performance analysis because most of this code is not hot. So what we really want is to be able to sort this by hotness. And we already have hotness available in the compiler with PGO. So if PGO is enabled, we can just use that and basically stick it into our optimization records. And this is what I've done. And the way it works is that this analysis pass becomes user of block frequency info, which is how block frequency is exposed to the rest of the compiler. And it's hooked up to a new mechanism called lazy block frequency info so that we avoid populating all this information unless we're actually generating optimization records. And then with this, the record will gain a new field called Hotness, which is the P2 execution count. And then Hotness appears on the index page, and then we sort the remarks by Hotness. And it also appears in a new column on the source view. Now this is relative hotness, as you can see. And it's relative in terms of the maximum hotness that we encountered in the data file. So this is not the percentage of total time that profilers normally would use. So this requires a bit of a mental adjustment when you read it, but it's still super useful. As I said, I wanted to broaden the scope. So initially, we only had these optimizations emitting optimization remarks. Now we have a bunch more, but there's a lot more that needs to be added. So this is certainly one area that if you're interested in this work, please consider hooking up other optimizations to this infrastructure. And it's pretty simple. So what I wanted to do is to improve and evaluate the tool on something more substantial. So I picked the LLVM test suite because then I could show some examples here as well. And essentially, I wanted to evaluate the tool along a few questions and doubts I had when starting on this. So one was whether the information presented at this high level would contain sufficient detail to actually reconstruct what happened in the compiler, which is sort of one of the goals here. Two is, which is related to this, is when we can discover good and bad interactions between the optimizations. That's so important in the compiler. That's sort of the basic design principles, and we want to see whether this thing is actually working. And then, of course, like any performance analysis tool, I was interested whether with the improved visibility, whether we can find real performance opportunities. Okay, so the first example I want to show is from Drystone, and it showcases interaction of optimizations. So if we click on the hottest remark on the index page, it takes us to this function. It's called proc8, and what we see on the far right-hand side is a new UI element I have not introduced yet, and it's called inlining context. So if you think about what happens after inlining is that you inline your functions, and then you're going to be optimizing each inlining instance separately, which means that you're going to be remarks generated for each of those and pointing back to the exact same source line. What you want is you want to be able to analyze those separately depending on the context. So this is what this provides. For example, these remarks come from proc8, which is when this function was not inlined but simply optimized by itself. And the other ones when it was inlined into proc0. Now, if we just look at the ones that come from proc8, that is when this function was not inlined, we see two remarks. There's a first one, which is coming from the loop vectorizer, successful vectorization. But if you look at the for loop a bit more carefully, it actually has a constant trip count of 2. So it's not a very good idea to vectorize it with a vector with a for, because we're only going to be executing the scalar loop anyway. So that's already one finding. But actually, the one that I want to focus on is here at the bottom. And this is coming from GVN. And what it says, that the load of type i32 int is not eliminated in favor of a store because it's clubbered by another store. So as you can see here, just like in the inlining case, I have the instructions hooked up, so we can look at what they're referring to. So this is the store that we're trying to forward from. And as you can see, the memory location is identical. So we're trying to forward that int par I to our load and just get rid of the load. But we can't, because there's this intervening store here. Now, if you look at the location of the store, it's actually referring to a seemingly different location. When we look at the access type for all these accesses, they all end. So probably what's happening here is that type-based alias analysis is making a conservative decision and just based on the access type and prevents load elimination. So let's look at what happens when we inline this function. Interestingly, the loop is optimized differently now. It's recognized as a memset idiom and replaced with a memset call. And then we delete the original loop. Obviously, this is still not perfect. What we really want here is just completely unroll this loop and remove it. But going to the case that we were looking in the previous example, the GVN case, what we see here is that now it's successful. So we're able to eliminate the load. For the reasons, we have to look at the call side. And that's, again, linked up. So you can just go to the call side, and the link takes you here, where you see that this function is invoked with two distinctive globals. So that means, and then it's basically propagated into these locations. So what's happening here is that with basically more precise alias analysis, global modref analysis was able to disambiguate these two accesses, and because of that, remove the load. So what we saw here is that without low-level debugging, we were able to quickly reconstruct what happened. And we were able to do this even though it involved interaction between multiple optimizations, inlining, alias analysis plus GVM. I also want to point out the particular GVM missed optimization remark that we had there. There I performed a little bit of extra analysis in order to manage false positives better, which is very important for any diagnostics. So first we get rid of trivial false positives. I mean, there are a lot of loads that we can't eliminate. We don't want to report all of them, but those where there's a chance that it can still be eliminated. So aliasing case is the primary example. Also, even if we report back to the user, we need to expose enough information so that the user can quickly detect if it's a false positive. So in this case, we had basically all the stores, all the interesting instructions hooked up so that the user can make a quick determination whether to pursue this or just move on to the next thing. Okay, so, oops, sorry. So my next example is from Freebench, and this is actually about finding performance opportunity. So again, if I just click on the hottest remark from the index page, it takes me to this function. And few lines into this function, there's this loop. And I'm not showing the entire loop, but basically the interesting part that we're concerned with. And if we look at the missed optimizations, the first one is coming from LLVM, so loop invariant code motion. And it says this: fail to hoist a load with a loop invariant address because the loop may invalidate its value. So effectively, we're loading from the same address in every iteration, but we can't hoist it out because we're not sure that the value is not changing in the loop. So if we look a bit more carefully, what we see that there's actually a lot more of this exact same message in this loop. So let's take a closer look. So in the first one, we're reading from a pointer called limpy. If you look at all uses of limpy here, what we see is that, and there's one further down, but basically we're not modifying this location via limpy. Of course, we could have pointers through other writes through other pointers that may invalidate it, but not through limpy. If we move on to the next message, it's using a different pointer, linD. And if you look at all uses of linD, again, we conclude the same thing. We don't modify the location through this pointer, but of course, other pointers could still do this. Now, if you look at this expression a bit more carefully, what we see here is that if linD is in fact loop invariant, this entire expression becomes loop invariant. And turns out this has a bunch of double precision floating point arithmetic instructions, including a division. So if we can hoist this out, that's probably going to be a profitable thing to do. So to summarize, we have these two read pointers that we're interested in hoisting out. But we have these other pointers that we perform writes through. And we have to make sure that these are independent in order to make for this transformation to be valid. And turns out, if you check the runtime values, these reads and writes don't alias. So this suggests that we could use loop versioning with array overlap checks. And in the version loop, we are safe to hoist out the loads. And we actually have an optimization pass that does this. It's called LLVM-based loop versioning. It's not on by default. So my first idea here was just let's turn it on, see what happens. So when we turn it on, recompile, regenerate the optimization view and then refreshing the browser, this is what we see. Actually, not much has changed. The LLVM cases are still red. But we have a new remark here that's coming from this pass that we enabled, which says that loop memory access is not suitable. So this, what means is that probably the analysis in this pass is not powerful enough to deal with this loop right now. But we were able to, at this point, we were able to identify the pass that we probably want to improve and sort of dig deeper with our low-level debugging. But in order to motivate that, it would be nice to know what's the performance opportunity associated with that. So the idea here is to approximate the opportunity by manually modifying the source to simulate this transformation. And for this, we're just going to add restrict to the two read pointers to tell the compiler that these reads can't alias with the writes. And if we, again, recompile at this point, regenerate the optimization view and refresh in the browser, this is what we see. So basically as you can see, all the LLVM cases turn green now. And not only that, in the expensive expression that we're looking at, we have additional LLVM cases for all the floating point arithmetic operations, including the fdiff at the bottom. And now at this point, we measure performance, and we have a dynamic instruction count reduction of 11% by making this change. And then performance translates 1 to 1, so we get a nice 11% headroom if we make this loop versioning improvement. So to summarize what we saw here, just like before, in this case, what we were able to do is find an optimization opportunity while staying in the high-level view of our tool. Again, we were able to reconstruct the reason for the missed optimization. Also, very importantly, because we were in the high-level view, we were able to notice those floating point arithmetic operations. So it exposed that the gain may be substantial. And also, when we actually made the change on the source code, we were able to get immediate feedback that we did achieve the desired effect. And then, of course, we were able to identify the next step, which is which path to improve. So I have the test results. I have actually results generated for the entire test suite at this URL too. So if you're interested in more examples, please check them out. So quickly, I want to go through where we are with the development. So as I said, the LLVM infrastructure pieces are all in place. The initial version of the tool is available upstream. I want to review what we still need to do to make this a good tool for compiler developers. But I also want to spend a little bit of time going back to that end user that I was mentioning in the introduction. Like what additional features we need to make this a good code author tool. And then there's a tangential here, which is that now that we're generating optimization records for the optimization viewer, we can use it to build actually new tools without the optimization viewer. So basically just new tools that could use optimization records. So, so regarding the status for compiler developers, so the tool is written in Python, which allows to just pull in rich functionality of Python. So for example, that's how the syntax highlighting is implemented. But we still need to hook up new passes. We also need to do what I did for GVM, which is sort of improve the diagnostics with sort of false positives in mind. And this may require a little bit of extra analysis. And of course, improve the UI. And on any of this, if this work is interesting to you, I encourage you to help out or just talk to me after the talk. Now for code authors. So what I was doing when going through the examples is that based on remarks from the optimizations, I was sort of reconstructing in my head what was happening. For users, we have to be more explicit. We have to actually tell them what we think has happened, and then also suggest specific actions that they can take to fix the problem. For example, in the LLVM case, we could say something like, if the 2 pointers can never point to the same object, consider using restrict. Also, we can add new analysis passes of a new type I call recommendation passes that could detect opportunity rather than actually perform the transformation and effectively suggest things like add source annotation to enable off-by-default passes. For example, aggressive loop transformations and non-temporal store optimizations, which are optimizations that can be hugely beneficial, but can actually hurt performance as well. So most of the time you want them under user control, but we can call attention to them if you detect a high confidence opportunity. Also, for optimizations that we actually don't have because it's extremely hard to get them right, like data transformations, we can detect them and suggest refactoring. Again, this is an area just being explored, so help is welcome. Now, moving on to the ideas about new tools that we can build on top of optimization records, aside from the optimization viewer tool. So there's actually already one tool that's done. Hal Finkel added an LLVM up report tool, which prepares listings for the source files with inlining certain optimizations that happen. So effectively sort of a text version, simplified version of this tool. Then we can also use this for performance regression analysis. So if you have the optimization records generated before a regression and after, and we write a new diffing tool that provides the different in optimizations in the same YAML format, then we can use the OpViewer tool to display what optimizations have changed, and that should hopefully help us to quickly track down the regression. Also, we can up-level these events into something like LLVM statistics, where if we see at the high level, at the aggregate level, some patterns that we're interested in, we can still zoom in all the way down to the individual events. With the added benefit that we have hotness information, so we're going to be focusing on code that matters. There's also another opportunity that's I think very interesting. I call this bottom-up search for performance opportunities. What I mean by this is that initially when I introduced how you look for improvements, that's what I call top-down. When you identify a bottleneck and then you try to find the matching optimization. In this case, we actually have an optimization or a missed optimization in mind, and we're trying to see how many times it actually occurs. So for example, if we want to look at how many times the same LLVM opportunity occurs in practice that we see in Freebench, and assuming we have all this data loaded into a relational database from our optimization record files, we should be able to just issue this highly hypothetical query that should tell us, which should give us basically all the instances where this happens, and ordered by hotness, so that we start focusing on the important stuff. And the nice thing about this, that it's going to find us different opportunities that occur with high frequency, but not necessarily in the hottest code. So before wrapping up, just want to acknowledge a few people that helped with this work. So Tyler Nowitzki added optimization remarks for the vectorizer, so did a lot of the foundations. John McCall suggested originally the idea of storing all this information in an external data file in YAML for post-processing. And then Hal Finkel helped throughout this work, did the LLVM up report tool, and many code reviews. And with this, I'm ready to answer questions.
Any question?
Hi, my name is Hideki. I work in the Intel's vectorizer, and I did a presentation yesterday also. So Intel's vectorizer actually has the diagnostic capabilities that is used by the vector advisor tool. That is actually a dynamic profiling tool that actually helps vectorize more code. And from that experiences, one of the most important things for the compiler developers to do to make this kind of tools very helpful is forget that we are the compiler developers when we are writing the diagnostic messages, because those needs to be interpreted by the regular programmers who never was compiler developers. So that's very important, and that's very time-consuming work. So we spend years cleaning up many of the messages that the compiler developed. So that's very important.
Sure.
But overall, I like your presentation, I like your work, and this is a great work.
Okay, thank you.
And one question actually.
Sure.
Is that are you keeping track of the loop transformations and different versions of the loop, same loop? So
that's an excellent question. So that's the next thing actually on my list to do. So anytime, basically what I described on the inlining case applies to loops as well, because we version them. Vectorizer would create the vectorized version and then the remainder loop. And again, whatever optimizations we do afterwards, going to be pointing back to the same source code. So it's that is still pretty confusing. So I was actually talking to Hal about this yesterday. I think what we want to do this is, as we version, use the loop ID metadata and really create separate ones. I think right now we just basically copy them. So it's the same ID. We end up with the same ID on all the version loops, but create unique ones so that we can track the different instances and sort of have version loop context or loop context column as well, or something like that. I mean, I'm not sure about the UI piece, but definitely it's something we need to track.
Okay, so one big caveat there is completely unrolled loop, because
yes.
you cannot tag into the loop ID. So
yes.
Please be careful there.
Okay, that's good. Thanks.
So any other questions?
So as a user, if I want to know which optimization is more important for a particular application or and some input set, how do I know it?
Which optimizations are important?
Yeah, so let's say you have a loop, you have multiple optimizations like loop interchange, loop fusions, but how do I know which optimization is more important?
I mean, that's, so one answer is the recommendation pass. I think that could do some analysis, additional analysis, and report something more sophisticated than just saying, I couldn't interchange, I couldn't do this and that. And I think the other thing is the analysis part of the message. So what appeared on the right-hand side. I think we can have, I think initially something that's useful for compiler developers, like really describe how high of a confidence we have that this transformations would be beneficial. Like for example, for data transformations, if we know that the structure size is pretty big, we're only accessing a single field, and with PGO we know it's a high trip count loop. we have good indication that maybe splitting up that structure into individual arrays may be a beneficial transformation.
So one last question. Do you have? Yeah.
So last year, I think Gerolf presented some info on like these Herculean over-the-top optimizations that the compiler might not necessarily do. So the current infrastructure basically says, we missed something, this has been implemented in the compiler. Do you foresee it being a case where we actually write analysis passes that will never do a transformation, but they will suggest these?
That's precisely the recommendation pass. It's an analysis pass, so it's not going to change the IR, but it can. And I think the first example that I was considering for that is it was actually non-temporal stores, because we know that those can be hugely beneficial, but also really hurt performance if there's actually temporal locality.
So thank you, Adam.